Here's a riddle for you. Let's say you and your friend challenge each other to a contest on a circular track. If you are smart about it, what location would you pick? Would you pick the inner track or the outer track as your starting point? Here's another riddle for you. Let's say you are a bird that was unfortunate enough to fly into this windmill here. Would you take more damage if you hit the tip of the moving windmill or the center of this moving windmill? The answer to both of these questions gives us some insight into the concept of angular velocity and linear velocity. And it is these concepts and their relationship to each other that we will pursue in this session. So here we have an object. It is an amorphous object. It has no definite shape. And this object is a collection of particles. So we have particles like P1, P2. We have an infinite number of possible locations inside this 3D object, and it is located in three-dimensional space. So we have the x-axis, the y-axis, and the vertical z-axis. And the object is spinning about the z-axis. Now in this case, let's pick up any particle, any one particle. For example, in this case it is P, which is situated at a radius r from the center or the axis of rotation. In this case, this object has two velocities. It is moving around and round and round. So the angle that it is tracing in a given amount of time is clearly changing. And it also has a tangential or linear velocity, which is given by vector v. The linear velocity tells you how fast the object is moving in a given direction at any moment of time. Do note, we are speaking about rotation here. So the direction of the object is constantly changing. So the linear velocity of the object is the instantaneous velocity of the object in the tangential direction at that moment of time. Now, delta theta is the angular displacement of the object, of this particle from the center of the rotation. It is sweeping an angle in a given amount of time, which is given by delta t. If we take the ratio of the change in angle for that particle and the change of time, the amount of time it took for the particle to trace this path, we get a value called the average angular velocity of this point with respect to this coordinate system. Remember, this is the average value. The instantaneous value of rotation may change within this interval. We will just have to look a little deeper. Now, angular velocity gives us an idea of how fast or slow an object is spinning or rotating. So it is a mathematical method for us to describe rotation. So angular velocity means the rate at which an object rotates. It gives us an idea of how fast an object or particle rotates with respect to a given point. Now coming back to our 3D object, we can say that if I take delta t to be an infinitely small amount of time, an infinitesimally small amount of time, such that delta t starts to approach zero, not exactly zero, but a vanishingly small amount of time, the equation delta theta by delta t turns into d theta by dt. So we are differentiating the angle with respect to time. This ratio d theta by dt is the instantaneous angular velocity, which is given by the symbol omega. So omega is the instantaneous angular velocity of this particle, which is rotating around the center of rotation c, and the linear velocity of this particle, the tangential velocity of this particle, is given by v is equal to omega r, where v is the linear velocity and omega is the angular velocity, and r is the radius of the circle. You may have already begun to suspect that while theta and t will maintain the same ratio for any given rotational velocity, the distance r from the center of the rotation is changing, which should have an effect on the linear velocity of this object. Let's see how this happens. So here we have a collection of particles. We have P1, which is at some distance from the center. We have P2, which is at a greater distance from the center. And we also have P3, which is exactly at the center, the axis of rotation. What will the location of these particles, what effect will this location have on the rotational speed or the angular speed with the linear velocity of these particles? So we can see each of these cases separately. So Vi is equal to omega Ri, where Vi is the linear velocity under observation and Ri is the distance from the center for that particular particle that we are considering. For example, if we look at the sense of rotation of these particles, which are moving either in the clockwise direction or the anti-clockwise direction, we can call the clockwise rotation to be negative and the anti-clockwise rotation to be positive. What will be the effect of the location of these particles on the actual linear velocity? In this case, let's start with the particle at the center. In this case, the radius of its orbit or the radius of the circular motion is 0 because the particle is at no separation from the center of rotation, as you can see here. In this case, r is equal to 0. Since v is equal to omega r, we notice that the tangential velocity for this particle is 0 because it is at 0 distance from the center of rotation. On the other hand, if we take a particle which is farther away, for example, if we consider v1, that is the linear velocity of the particle at point p1, we notice that it will have a finite value because in this case, the radius is not 0. Again, if we take another particle, let's say we take particle p2, which is at a greater distance from the center of rotation, we notice that its value of linear velocity is v2 equal to omega r2. In all of these cases, you will notice that the rotational velocity or the rotational speed of the particles is identical, it is omega, but we are also seeing that the velocities are changing because the radius from the center is changing, which means that for a given value of rotational velocity, the linear velocity of a particle will depend on the distance of the particle from the axis of rotation. For example, in this case, you observe a mechanic who is wrenching a nut using this wrench. You will see that while the mechanic is rotating the wrench, the center of the wrench will move a lot slower compared to the end of the wrench where his hand is located, even though the entire wrench is tracing the same angle in the same amount of time. So the rotational velocity of the wrench omega is constant, but the velocity of various points on this wrench will depend on the distance of that point from the center of rotation, which in this case is a screw. Now, how do we assign the direction of rotation? As I said previously, we consider anti-clockwise rotation to be positive and clockwise rotation to be negative. In this particular case, we can use a handy rule called the right-hand rule, which says that the direction in which your finger is oriented and the direction in which your other fingers are curling will tell you whether the rotation is positive or negative. So in this case, you will notice that the fingers are curling in the anti-clockwise direction, and as a result, we consider the axis of this rotation to be positive. So the magnitude of angular velocity is given as d theta by dt equal to omega. So it is the instantaneous rate of change of angle with respect to time. Looking at this in a little more detail, we are looking at different vectors here. We have the rotation vector, that is omega. We have the tangential vector, which is v, and we have the distance of this point from the center of rotation given by r1. So in this case, if we observe the formula, we notice that omega cross r is equal to omega multiplied by OP. The cross product of these quantities can give us some idea of the linear velocity of the particle at that instant of time. So we can say that the relationship between the angular and linear velocity is given as v is equal to omega cross r. So the cross product of the rotational velocity and the radius of the particle will give us the linear velocity of the particle at any instant of time. Coming back to the riddle, if you were one of these two kids, which kid would you want to be? Well, if you are on the inner track, you are closer to the center around which you are going round and round, which means that you can maintain the same angular velocity for a lower value of linear velocity. On the other hand, if your friend is on the outer track, he or she will have to trace a longer arc in the same amount of time. So in order to keep up with you, they will have to travel at a faster linear speed. So if you are someone who likes to win bets, it is better for you to choose the inner track rather than the outer track. But this leads us to a question. We understood how linear velocity and rotational velocity works, but what causes an object to rotate about an axis? This is what we will explore next. So, to summarize everything we have done, let's see at what all things we have covered in this session.
Manorama Horizon. Learning made simple.